Have you ever wondered what's actually happening when the ground starts to shake? Well, today we're diving deep into one of nature's most powerful forces, earthquakes. We're going to figure out what's going on miles below our feet, how all that energy gets released, and, maybe most importantly, how we even begin to measure something so massive. So let's start with the big question that's going to guide us through this whole thing. When you hear about a magnitude 7 quake, you probably pictured total chaos, right? But is the raw power of an earthquake the same thing as the damage it leaves behind? The answer, you'll see, is a lot more interesting than you might think.
To get to that answer, we have to start at the very beginning. We need to go deep underground to where all that incredible tension is building up right under our feet.
And it all starts here, along something called a fault. Now don't just picture a simple crack in the ground. A fault is a massive fracture, a huge break in the Earth's crust. It's basically a battlefield where enormous geological forces are in a constant grinding tug of war.
So how does this whole thing play out? Well, you can think of it in 3 steps. First, you've got pressure. Massive blocks of rock are trying to slide past each other, but, and this is step 2, they can't. Friction, just the roughness of the rock, is holding them stuck. So they start to bend and warp, storing up energy like a tightly coiled spring. And then, step 3, the snap. The pressure finally becomes too much, it overcomes that friction, and the rocks suddenly lurch forward, releasing all that pent-up energy in one gigantic burst.
And that sudden, violent release of energy is what sends shock waves, we call them seismic waves, blasting outwards in every direction, kind of like the ripples you see when you drop a stone in a pond. This exact moment, this is the birth of the earthquake.
Okay, so the energy is out. It's on the move. Now let's actually follow its journey from way down in the earth all the way up to the surface where we are. Where does it go first?
You know what's interesting? An earthquake doesn't really have just one single location. To really get it, you need to know about 2 totally different but connected points. Its true origin deep underground and that spot on the map you always see on the news.
Let's break those down. First, you have the hypocenter, which is sometimes called the focus. This is the actual spot deep in the crust where the rock snapped. It's the real birthplace. Then you've got the epicenter. That's the point on the ground, on the surface, directly above the hypocenter. Think of it like the hypocenter's shadow. And it's called the epicenter because it's the very first place on the surface that gets hit with those seismic waves.
So does it matter how deep that hypocenter is? Oh, absolutely. It matters a lot. Shallow quakes, we're talking less than 60 kilometers down, are way more destructive. Think of it like this. If someone shouts right next to your ear, it's going to be loud. But if they're shouting from across a huge field, the sound is going to be much weaker by the time it gets to you. It's the same idea. Waves from a shallow quake have way less ground to travel through, so they hit the surface with a ton more energy.
Now, you might assume that all earthquakes come from those natural shifting plates we just talked about. But it turns out the story is a little more complicated than that. Some shakes are natural, and some, well, some are on us.
Yeah, check this out. While the grinding of tectonic plates is the cause for most earthquakes by far, they're not the only game in town. Things like volcanic activity, the collapse of a huge mine, or even big explosions can also make the ground tremble.
We can basically sort these into 2 big buckets. You've got your natural causes, tectonic, from those sliding plates, and volcanic, which is caused by magma moving around under a volcano. But then you have what are called anthropogenic, or man-made causes. This can be a collapse quake from the roof of a giant mine caving in, or an explosion quake from something like a nuclear test. There are even reservoir-induced quakes, where the sheer weight of the water behind a massive dam can put new stress on faults deep below.
All right, so this brings us right back to that big question from the beginning. How do we actually measure these things? How do you put a number on an event that powerful? This is where we finally untangle that difference between an earthquake's power and its destruction.
And it turns out there are 2 completely different ways to do it. The first is magnitude, which you've heard of. That's the Richter scale. It's all about one thing, the total raw energy released way down at the hypocenter. The second is intensity, which uses the Mercalli scale. This one doesn't care about the source energy at all. It only cares about the effects, what people actually saw and felt up on the surface.
So let's put them side by side. The Richter scale measures energy with an instrument, a seismograph, and gives you one single number for the entire earthquake. A magnitude 7 is a magnitude 7, period. But the Mercalli scale, it's totally different. It relies on human observation, looking at damage, talking to people. This means one earthquake can have lots of different Mercalli values. It might be a I9, total devastation, at the epicenter, but only a I4, just some rattling windows, 100 miles away.
Exactly. The Mercalli scale is all about the human experience. It's not about some abstract energy calculation. It's about what you would actually feel and see, from a slight rattle of your windows to total destruction. It's built to answer the question, so how bad was it right here?
Okay, but back to the Richter scale for a second, because the numbers can be really deceiving. It's a logarithmic scale. Now, what that means is that each whole number you go up isn't just a little bit more powerful, it's a giant leap. A magnitude 6.0 isn't 1 degree stronger than a 5.0, it releases about 31 times more energy.
And the scale of that energy is just mind-blowing. To put that into perspective, a magnitude 8.0 quake unleashes the same amount of energy as over 56 million tons of explosives. That is way more powerful than the biggest nuclear bomb ever tested. That's the kind of raw, planetary power that the Richter scale is trying to capture.
So there you have it. We've got magnitude to measure a quake's raw power deep underground, and we have intensity to measure its real-world effects on us. We've finally untangled the difference. But it all leads to an even bigger challenge, doesn't it? We can measure these things with incredible precision after they happen, but will we ever be able to predict them before they strike?